Okay, in this clip we want to talk about still the implicit function theorem, but now for systems of equations. So let me write what a system of equations is. So system, right? So suppose we have not, remember we had f of xy or f of xyz equals 0. That was the relation from which we wanted to extract an implicit function. So now we're going to have f1, that's going to be the first relation, and it's going to be a relation of many variables, and we're going to say what many is in a minute. I'm going to call the variables x1 up to xn, and then there are going to be more variables, which I'm going to call z1 up to zm. So there's a total of n plus m variables. They play different roles, so I'm giving them different names, but they're just n plus m variables. So here's the first relation, and then there's another one, f2 of all these variables, x1 up to xn, and z1 up to zm equals 0. And then there's a bunch of these relations, total of m of them. So m has to correspond to the number of variables I called z. So x1 up to xn, z1 up to zm equals 0. So here's a system of m relations or equations involving n plus m variables. I'm of course assuming that all these f's are C1, everything is nice and smooth. Okay, now I'm going to define, so remember what the conditions for the implicit function theorem were. There was this specific partial derivative that was not allowed to vanish, right? And the derivative was the derivative of the relation of the big F with respect to the variable which we wanted to isolate as a function of the other variables. Remember that? So if you wanted to write y as a function of x and z, the derivative with respect to y had to be non-zero. Remember that? So that condition is going to be replaced now by a bunch of conditions on all these derivatives, okay? And the partials are going to be with respect to the z variables. Let me hint where I'm heading. I want to write the z's as a function, as functions of the x's. Okay, that's what I want to do here. So I'm going to define delta to be the determinant. Remember what the determinant is? It's this complicated relation on the entries of the matrix, right? Okay, we studied determinants, for example, 3x3 determinants when we discussed the vector product. Remember how the vector product was given? Okay, so the determinant of this very big matrix, df1 to dz1, df1 to dz2, all the way up to df1 to dzm. And then in the second line, I'm going to take df2 to dz1, df2 to dz2, all the way up to df2 to dzm. And then there are going to be m lines. So it's a square matrix, m by m matrix. And at the end, I have the partial derivatives of fm with respect to the z variables. dfm to dzm. Okay? So the determinant of this thing, what you have to do in general, we're going to do a more user-friendly example. You have to calculate all the derivatives of all the f's with respect to all the variables which you want to express as functions of the other variables. And then you have to do this complicated thing called a determinant, which I'm not going to remind you of what it is in general, because the most we're going to encounter is usually going to be 2 by 2 and 3 by 3, and those we know already. Okay, we'll see an example in a minute. Okay, in your algebra course, for those of you that are taking the algebra course in conjunction with this course, you'll discuss determinants in general and how they're defined, and for any square matrix and how to calculate them. Okay, so I don't want to take the fun away from your algebra teacher. Okay, so I'm calling this thing delta, okay, the determinant of this matrix. And now the theorem is the following. This is the implicit function theorem for this situation. If delta is non-zero, then, well, non-zero where? You calculate this determinant, it's going to be some huge expression involving lots and lots of functions of lots and lots of variables, right? And then you plug in the values of these variables, and you have to check that it's non-zero, okay? So where? At the point around which you want to write the z's as functions of x's, okay? So I'm going to write that point in a minute. Then in a neighborhood of, let's call the point x 0 bar, z 0 bar. x0 is a vector whose components are x1, x2, x3 up to xn. And x is a vector whose components are x1 up to xn, and x0 is a specific point with n coordinates. Z is a vector whose components are z1, z2 up to zm, and z0 is a specific values for each of these z variables. So is it clear what I wrote here? It's specific values for all the x variables and all the z variables. Clear? Okay. Then in a neighborhood of this point, there are unique functions. Zi, each of the z's can be expressed as a function, which we're going to call fi, of the x variables, of x1 up to xn. Okay, Zi equals fi of x1 up to xn, where I ranges from 1 all the way up to m. So there are m implicit functions here. There are unique functions Zi, where Zi, each of them is a C1 function, continuous partial derivatives. And I'm going to write this a bit vaguely. I don't want to get into the precise details, but we'll see in an example how we do it. And the partial derivatives. So remember the implicit function theorem, the one equation one, gave us a formula to calculate the derivatives. Remember? It was minus df to dx divided by df to dy. Remember that sort of thing? So now there's going to be an analogous statement, which I'm going to write a bit vaguely, and the partial derivatives of the zi's, of fi, of these functions, can be calculated using what's called implicit differentiation. Okay? And we're going to say what that is in a second. Implicit differentiation. Okay? Let's do an example before we say anything else, so that you see that this is not just a scary two-board statement, but it's very, very practical. Okay. So maybe before we do an example, let's do a mini example of what do I mean by implicit differentiation. So mini example of implicit differentiation. So I want to remind you one example that we had previously. We had, recall that we had the equation 3x squared y minus yz squared minus 4xz minus 7 equals 0. Remember we had this example? And we managed to show that we can write y as a function of x and z, and we found the derivative of that function with respect to x, and we showed that it can be done using the implicit function theorem, and then we showed that it in fact can be done in this example explicitly. Remember that, everybody? Okay. So what I want to do is show you how you can find the derivative by implicit differentiation. So recall, this is the relation. This is capital F that I'm looking at. Let's add that. Let's write f of x, y, z was this thing. Recall. And what do I mean by implicit differentiation? So suppose we have y equals a function of x and z. Okay, suppose we showed that that exists, for example, using the implicit function theorem. Okay, so we don't know the formula for it. If we knew the formula for f, it would be easy to take the derivatives, right? But suppose we just know it exists. Okay, so the implicit function theorem told us how to find the derivatives, for example, the derivative of y with respect to x, by considering the derivatives of f minus df to dx divided by df to dy. Remember that? Okay, so now I want to do it in a different way. Okay, we can find partials of f using this so-called implicit differentiation. What do I mean by that? I mean, I'm going to take this equation and take the derivatives of both sides, for example, with respect to x. Okay? So let's take the derivative of this equation, of both sides of this equation, with respect to x. Okay? But remember that I'm thinking of y itself as a function of x and z. Okay? So what's going to be the derivative of 3x squared y, where y itself is a function of x and z? So the derivative with respect to x just of this term is going to be 6x times y plus, it's a product. It's a product of two factors, both having x's in them. 3x squared obviously has x's in it, but y also has x's in it because we're thinking of y as a function of x and z. So I'm using the product rule. The derivative of 3x squared is 6x times y untouched plus 3x squared untouched times the derivative of y with respect to x. Because y is now a function of x. Clear? And then I'm doing it for this as well. So here, z squared does not have x's in it, but y does. Y is a function of x and z. So the derivative of this thing is minus dy to dx times z squared. The derivative of this thing with respect to x is minus 4z. This is just a scalar, no derivative, equals 0. Is it clear what I did and why I'm calling it implicit differentiation. I'm regarding y as a function of f of x and z, and then taking the derivative with respect to x of both sides. Clear? Everybody good? Okay. Now from this, I can isolate what dy to dx is. Okay? So notice that I don't know what this function is, but I can isolate what its derivative is. Okay, so what do I get? I get these two I can pull out dy to dx from, times, so let's throw the other ones to the other side. So I'm going to get 4z minus 6xy, and then I have dy to dx times this thing, so I'm going to divide out by it. 3x squared minus z squared. Do you agree? Clear? So I found the derivative of f with respect to x, of y with respect to x, by implicit differentiation. Clear? Now in this example, and we'll get the answer is going to be minus 14, and then you're going to remember that we did this example, right? Remember minus 14, that's something you can't forget, even if you forgot everything until now. So dy to dx calculated at, the point we calculated at was negative 1, I can write it like this, negative 1, 2, that was the point where we calculated. So when x is negative 1 and z is negative 2, y is a function of x and z, when x is negative 1 and z is 2, the y has to be 1. That's how this point originated as negative 1, 1, 2. And therefore, it's this thing evaluated at, so let's write it, 4z minus 6xy divided by 3x squared minus z squared, evaluated at negative 1, 1, 2, right? The first condition of the implicit function theorem was that f of x0, z0 is y0. Okay, we looked at the point negative 1, 1, 2, so f of negative 1, 2 is 1, is the y coordinate of that point. Okay, so that's why we get this point. And what we get, let's plug in the values. 8 minus plus 6 divided by 3 minus 4, and here's our negative 14. Good? So this is what we call implicit differentiation. Okay? Now let's do an example for a system of equations. So here's no longer a mini example, but an example of a system of equations. So it's not going to be a complicated example. There are going to be only two equations, and there are going to be two variables involved, which are the x's, and two more variables, which are the z's. Okay? So here's the system. xu plus yvu squared equals 2, and xu cubed plus y squared v to the power 4 equals 2 as well. Okay, so do you see two relations, first of all? And do you see that there are four variables, x, y, u, and v? Okay, so let's show that near the point x, y, u, v equals 1, 1, 1, 1, near this point, we can express u, and v uniquely as functions of x and y. So I want to write u as a function of x and y, and v as a function of x and y, such that when I plug them in here, they satisfy these two relations. Okay? Do you see the spirit of the implicit function theorem applied to something more general? Clear? Everybody with me? You're very quiet. Good, everybody? I want to express u and v as functions of x and y, such that when I plug them into here, they satisfy the relations. Okay? That's an implicit function. When it's written like this, they're not functions, right? They're just all intertwined, tangled with one another. Clear? Okay, so let's do that. So I have to set this thing into the format of that theorem. So the theorem is going to have two relations, f1 and f2. f1, both of them are going to be relations of the four variables. X and y are going to be in the role of the x's, of the variables that I want to write the other variables as functions of them. So x and y are going to be x1 and x2 in that format, and u and v are going to be z1 and z2 in that format. Okay? So what is f1? f1 is this thing, x u plus y v u squared minus 2. And f2 is x u cubed plus y squared v to the power 4 minus 2. These are the two relations. Okay? In order to guarantee that I can do this, I'm not going to get explicit formulas. I'm just going to get a statement that it can be done. And what do I need to check? I look at the theorem. The theorem said, well, you have to check that that delta thing, that determinant, is not 0. Right? That's what I have to check. So let's calculate it. What is delta? Delta is the determinant. How many entries is this matrix going to have? Two by two, exactly. There are two f's and there are two z variables. Do you agree? So it's going to be df1 to du, df1 to dv, df2 to du, df2 to dv. Good? Clear? Okay, let's calculate them. What's df1 to du? It's x plus 2yvu. Do you agree? What's df1 to dv? It's yu squared. Good? What's df2 to du? 3xu squared. That's it. And what's df2 to dv? 4y squared v cubed. Clear? How do we calculate a 2 by 2 determinant? It's this times this minus this times this. Remember that? This times this minus this times this. So what do we get? Well, we don't, okay, we can, before we do that, it's actually easier to plug in the values first, right? What do we want to verify? We want to verify that this thing at the point we're interested in is not 0, right? At this point, okay? So what's this thing, this determinant, evaluated at this point? I just have to plug in 1, 1, 1, 1 for all of them, okay? So when I plug in 1, 1, 1, 1, what do I get? 1 plus 2, I get 3 here, 1, 3, 4. Do you agree? So let me write that here. This determinant evaluated at the point 1, 1, 1, 1 equals the matrix what did we say? 3, 1, 3, 4. And it's easier to find the determinant now. It's 12 minus 3. It's 9. And 9 has this wonderful property that it's not 0. Clear? Everybody good? Okay. So at this point, what we know is that the conditions of the theorem hold. Well, we have to check that these are C1 functions, and they are. So the conditions of the theorem hold. Okay. Oh, and we also have to check that the point satisfies these relations, right? That was, I even forgot to write that. That's the basic thing to check. Okay, so does the point satisfy? 1 plus 1 equals 2. Did you ever think you'd calculate 1 plus 1 equals 2 in Calc 2, in the Technion? Wow. And 1 plus 1 equals 2 again. Did you ever think you'd do it 2 times in a row? Good, everybody? Okay, so this point satisfies the relation. The functions are C1. The derivative condition, which is this determinant, does not vanish. Therefore, we know that we can do this. Okay, so let's write that. So by the theorem, we know there are C1 functions, U as a function, call it f1 of x and y, and v as a function, you can call it x2 of x and y. Good? Everybody with me? Questions? Good. Is everything just crystal clear, or are you just totally out? Ask. If there are questions, ask. So I'm getting both kinds of looks. Go on, and help. Ask. You have to ask questions if you want me to help. Do you see, Ami, I'm going to jump between boards a bit, please follow me. Do you see that the example that we had fits into the framework of this theorem? We had only two relations in that case, involving 4 variables, x and y, u and v. X was x1, y was x2, u was z1, and v was z2. Why am I saying that? Because I want to express the z's, u and v, as functions of the x's, x and y. Okay? The theorem told me, if your 2 relations, or m relations in general, are C1 functions, they are. If the point you're looking at, that I forgot to write, but if the point you're looking at satisfies both relations, okay, those are precisely the conditions of the implicit function theorem for one relation. Okay? Satisfies them. We check that as well. Then, I'm moving on to this board. There's one more thing you have to check, which looks very scary in general, but boils down, in the case of 2 relations with 4 variables, to a 2 by 2 matrix. Okay? Check that the matrix of the derivatives does not vanish at the point you're interested in. Okay? So that's the determinant which we calculated. The derivatives of the f's with respect to the variables which you want to write as functions of the others. Okay? Then, there are unique functions. U equals f1 of x and y, and v equals f2 of x and y. Good? Everybody? Okay, wonderful. Where we know the functions are C1, and that we didn't do yet, we want to calculate the partials now. Good? And the partials we're going to calculate using implicit differentiation. We'll see that in a second. Yes?
So are you allowed to break it down into as many different equations, like dependent on, if you had another equation, could you make it all dependent on just x and just have 1 x and 3 z's? according to the formula?
No, there's some correspondence that has to hold between the number of equations and the number of variables you can extract as functions of the others. That's the number m. Okay, so if you have m equations, you can express m variables as as functions of the other variables. It has to be a square matrix here. M relations, f1 up to fm, m variables, which are going to be functions of the others, z1 to zm.
So if
Okay.
if you were given another function in this example, would you be able to write everything in terms of just x?
Providing all the conditions of the theorem hold. Yes, sometimes yes. Okay, it depends on yeah, so I don't know to answer in general, but if all the conditions hold, then you should be able to write, yes. Okay, yes.
So we don't know how to find the function itself, but we're going to know.
We don't know how to find these functions,
But we know the derivative.
but we have a way of calculating the derivatives, just like in the implicit function theorem for a single equation. Okay, we didn't know how to find f of xy or f of xz in that example. Sometimes we do know, not by means of the theorem. Sometimes we just know how to solve it for y or solve it for z, right? But if we don't, the theorem tells us there are. It's an existence theorem, plus a little bonus. You can find the derivative. Okay, let's see how we find the derivative using implicit differentiation. So let's look again at this board. Here are the two relations, or you can look here, it doesn't matter. I'm going to take derivatives of these with respect to, I'll tell you what, I'll write it in a second. We're going to find, I'm going to do one of them, right? There are four possible ones. You can find the derivative of u with respect to x, and v with respect to x, and u with respect to y, and v with respect to y. Okay? We'll find the derivative of u with respect to x. That's the one I'm going to do. You can do the others on your own. How am I going to do it? I'm going to take derivatives of everything here, thinking of x as x, u as a function of x and y is y, v is again a function of x and y. So looking at this thing, I only see an x here. But looking at it more carefully, I see x's all over the place. There are x's here, and here, and here, and here, and here. Because u and v are now functions of x and y. Okay? And I'm going to take the derivatives. Clear? Is it clear what I'm going to do? So let's write that. So let's find the derivative of u with respect to x, or you can call it the derivative of f1 with respect to x, it doesn't matter, at the point 1, 1. Okay? So I'm going to take by implicit differentiation. Good? So how do I do it? Maybe I'll copy the original equations here, and then we can... So our system was xu plus yvu squared minus 2 equals 0. That was f1. And xu cubed plus y squared v to the power 4 minus 2 equals 0. Now I'm going to take derivatives. So I'll do it slowly. Tell me if you agree. So this is a product, x and u, because x has x's in it and u has x's in it. Okay? So the derivative by the product rule is u plus x times du to dx. Do you agree? That's the derivative of xu by the product rule. Plus, here again I have a product rule, because v has x's in it and u has x's in it. So the derivative is y, the derivative of v, dv to dx, times the u part untouched, plus y is just a scalar here. Now v untouched times the derivative of 2u. The derivative of 2u is, let's add the 2 here, the derivative of u squared is 2u times the inner derivative, du to dx. and that has to equal 0. Was that clear? Good? Let's do it for the second one. I'm taking the derivative of this product. Both factors have x's in them. The derivative of x is just 1, so I get u cubed, plus x untouched times the derivative of u cubed, which is 3u squared times the inner derivative, du to dx. Plus, now v has x's in it, so it's 4y squared v to the power 3 dv to dx. And that has to equal 0 as well. Clear? I'm verifying that I didn't make any mistakes. Nope, looks good. Good? Okay. What do I get? So this is now a system involving these derivatives, dv to dx and du to dx. And I want to find what du to dx is, right? Let's find du to dx at the point 1, 1. What are these variables? What are these this one and this one? Which variables are they? U is a function of x and y. So this one is x and this one is y. Do you agree? When x is 1 and y is 1, what are u and v? They're also 1, 1 because the point 1, 1, 1, 1 satisfied the relation. So u of 1, 1 has to be 1 and v of 1, 1 has to be 1. Clear? That's the statement of the theorem, that what we're finding are functions that satisfy the relation. Okay? So where do I want to continue? I need this. So I'm going to erase the top part and continue on the same board. Usually not a good idea, but otherwise I'd have to copy this. So when x, y, z, w, x, y, u, v, x, y, u, v equals 1, 1, 1, 1, we get, I'm going to plug everything into here. So what do I get? U is 1, 1, plus x is 1 times du to dx, which I don't know what it is, du to dx, plus y is 1, u is 1, so plus dv to dx, plus 2 times 1, 1, 1, plus 2 du to dx. This is v. And that equals 0. And from the other one, 1 plus 3 times 1 times 1 times du to dx, plus 4 times 1 times 1 dv to dx. And that equals 0 as well. Good? Therefore, this simplifies into what? 3 du to dx plus dv to dx equals -1, and 3 du to dx plus 4 dv to dx also equals -1. Good? Now it's a system of two equations in exactly two variables. I want to find what du to dx is and what dv to dx is. Actually, I declared that I'm only going to find du to dx, but I'm going to find both for the same money. So what do I get? How do you solve a system like this? You can, for example, subtract the equations, right? So I get dv to dx minus 4 dv to dx. So I get minus 3 dv to dx equals -1, -1 equals 0, right? Is that true? So dv to dx is 0. And therefore, I can plug it in either 1, and I get that 3 du to dx is negative 1. So du to dx equals negative 1/3. Okay, and that's all at the point, should emphasize, at the point 1, 1. Good? So this is called implicit differentiation. Questions? So don't feel bad with yourself if you feel a bit overwhelmed now, because that's kind of typical. This theorem, even without the system of equations case, is sometimes a bit scary. You have to get used to it, but it's not that bad. But then the system version of it is even more, looks more involved and scary. But I think if you read this over carefully, you'll see that we didn't do anything too complicated. Okay? We just took a theorem, verified the condition, see that all the conditions hold, and then did implicit differentiation, which is exactly what we did in that mini example before, just now for a system. Okay? And you'll do 1 or 2 examples on your own, and you'll see that it's really nothing to be afraid of. Okay? Questions? Good? Okay, so the last thing we want to do with implicit functions, is write another theorem that's going to follow from this theorem, from the implicit function theorem for systems. And that theorem is going to be useful in the future when we talk about totally different things like integrals. So that's coming up next.